Perth Linux Users Group, talking Linux and open source.
Good evening, everyone. Welcome to our regular talk. Good evening, everyone. Welcome to our regular monthly talk. Tonight we've got Kevin Vinsen from ICRA, the International, what is it, sorry?
International Centre for Radio Astronomy Research.
The International Centre for Radio Astronomy Research. He's going to be giving us a talk on the Pan-STARRS optical, no?
Square kilometre array.
The square kilometre array, sorry. Okay, great. So it's a little bit different to what we thought, but interesting nonetheless. Great, so I'll hand over to Kevin and let him start. Thanks, Kevin.
Oh, hi. My name's Kevin Vinsen. I'm from the Data Intensive Research Group within ICRA. Our task is mostly looking at the data problems and the computational problems about this beastie, which I'm about to tell you about.
The Hitchhiker's Guide to the Galaxy is a wholly remarkable book. The introduction starts like this. Space, it says, is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the street to the chemist, but that's just peanuts to space. Listen. And so on.
Douglas Adams was spot on. Space is really big. But we watch far too much Stargate and Star Trek. And we think it's easy to travel these distances. You know, I mean, you see Captain Kirk talk to Chekhov. Yes, Captain, I can be there in 5 minutes. It's only 4 light years. Yeah, it don't quite work like that. Here's our local neighbourhood. There we are. Sitting there. Anybody know where Betelgeuse is? The star Betelgeuse? It's in the constellation Orion. Now, if that star was in our solar system, the star would be that big. I mean, we're actually quite small, compact bijou compared to some of the others out there. Here's our local neighbourhood. There we are, Alpha Centauri. For those of you who are interested in Hitchhiker's Guide to the Galaxy, he wasn't lying. There's Barnard's star, where the Vogons were on their way to drop Ford and Arthur. There's Alpha Centauri, our nearest neighbour. Now, for those of you who are here, we have prizes. If you could travel at the speed of the fastest man-made craft, which was Helios 2, which was a solar probe that smacked into the sun at 250,000 kilometres an hour, how long to get to Alpha Centauri? Nearest 1,000 years will do. No, it's more than that. No, that's too big. We're getting closer. Down a little bit more. Which way is down? Down. No, down from 25. Clean your ears out, James. Spot on. First prize goes to... which is actually quite a long time when all's said and done. And then we have our galaxy. Ain't she pretty? You know, she's got a dirty little secret, though. She's a cannibal. She's eating these ones around the edges. And then, our nearest neighbour, Andromeda, M31. Off to the side there, it's around 2.5 to 3 million light years away. So, getting there will take a long time. Now, don't want to alarm you, but I do have some bad news. This is what's going to happen with our two galaxies. Run. Come on, run. Now let's try again. Run. And what you should see is a simulation from Kenji of the two galaxies smashing into each other, but my Mac is not playing ball with us today. Don't worry though, we're talking about 3 billion years away. And then we have our supercluster, there's where we are. But there's lots of clusters of galaxies, and this is some of the stuff we're interested in. Why does it form like that? Why do we see these tendrils of galaxies? Now, what have we been seeing? If we look at space and keep looking, we actually see more and more. This is the most cited image in astronomy at the moment. It's the Hubble Ultra Deep Field. All right. Another prize. Anybody want to make a guess how many seconds the exposure on that was? Seconds. In seconds. It was a million, which is 11 days. And what we found was we have to rethink a little bit about galaxy evolution. In the sort of the early 2000s, we thought there were sort of a couple of 100 billion galaxies out there. Then this came along. I mean, there's some really pretty ones. There's a nice little spiral sitting here. We've had to do a little rethink. We think there's probably about 500 billion galaxies out there now. And that's what we want to be doing with the Square Kilometre Array, is cataloguing these things. And just to put it into context, the screen's moved. Down the bottom here, you can actually see the area of the sun, this image compared to the moon. But unfortunately, can someone rejig the screen? Because we're losing all the bottom.
No, the screen's coming off there. It's your Mac's doing silly stuff.
Bloody Mac. Right. Leave it be.
In a remote and inhospitable desert, something incredible is being planned. Something that will enable us to explore the universe, its past, and its ultimate fate. A masterpiece of scientific engineering that will be the world's largest, most powerful radio telescope. The Square Kilometre Array. The SKA will detect radio waves to reveal the hidden universe and answer fundamental questions about the cosmos. Its overwhelming size will enable it to peer deep into space, back to a time known as the Dark Ages, before the first stars shone. The SKA will reveal how the first galaxies formed from huge clouds of hydrogen gas, and will reveal the origins of supermassive black holes at their centers. It will survey the sky 10,000 times faster than existing telescopes to create a 3D map of galaxies in space and cosmic time. This map will help us understand how galaxies evolve and how the acceleration in the expansion of the universe is driven by a mysterious dark energy. The SKA will search for gravitational waves, ripples in the fabric of space-time, by monitoring pulsars, the collapsed spinning cores of dead stars. These gravitational waves are generated when supermassive black holes interact. The SKA will also investigate how gravity behaves close to black holes.
Placement again, as a highlight.
The unique sensitivity of the SKA will enable the study of radio emissions from the early universe that have passed through magnetic fields in space. This will help identify the origins of cosmic magnetism, a fundamental force difficult to study at other wavelengths.
And remember that, because that will bite us in a bit.
And through its ability to detect organic molecules and investigate how other Earth-like planets are formed, it might even answer the question, are we alone in the universe? The SKA will revolutionize our understanding of the cosmos. It will take us on a voyage into the unknown. Who knows what else it may reveal?
So there's the bigger picture. That's what we're trying to build here. All right, a little bit of science for you. Sorry to do this to you, but the radio spectrum. We have a great atmosphere. It keeps an awful lot of rubbish out. We really don't want gamma rays, ultraviolet, coming through because it would just fry us to a crisp. But there's this tiny little gap here where optical light comes through. It's about 390 to 750 nanometers, which is really actually quite small. But then there's this huge bit here, which is radio. This is where radio comes through. See, you can see, we can see an awful lot with a radio telescope. And this is the little sucker we're interested in, hydrogen. When the electron does a spin flip, it emits a radio wave at 21 centimeters. And that's what we're looking for mostly. It's not the only thing we can see. Neutral hydrogen is the most thing, but we can actually see about 150 different molecules out there. There's about 500 lines we've also identified that we don't actually know what they are yet, but we're working on it. But I mean, some of the important things. We can see water. That's kind of important for us. Hydrogen sulfide? No, unless you want to make stink bombs. Methanol? Well, hey, that'll keep the bogans happy. But these two are the really interesting ones. Aminoacetylnitrile. That's an amino acid. That's the building blocks for us. And glycoaldehyde, it's a sugar. And we can see these in such quantities because there has to be it has to be a huge amount for us to be able to see it. And I'll explain a little bit later why. Now, let's just have a quick look at the difference between optical astronomy and radio astronomy. M81, M82, one of the most photogenic galaxies out there. Very pretty, very dense star formation region in the middle there. It's about 36,000 light years across. Now, vagary of the human eye, we see dark things on a light background better than we see light things on a dark brown background, which is why we have white paper and black pens rather than chalkboards nowadays. So there's the two of them sitting there together. We can now see a little bit more over here. Now, let's have a look at what the hydrogen tells us. This is what we see with hydrogen. Well, that's interesting, isn't it? Look, you can see tides. These galaxies are actually connected together. Let me just overlay the whole lot on top of each other so it makes a better image. So this is one of the big benefits of radio astronomy. We can see an awful lot more than the optical boys can. Because we're looking at the building blocks of stars and galaxies, the hydrogen. Now, radio photons, though, are wimps. They are the two stone weaklings on the beach. When an optical photon hits your eye, it puts in about 2 electron volts. A radio photon is about 2 million times weaker. Now, that's one reason why things like the Parkes dish have to be so damn big. We've got to catch these things. The other reason is angular resolution. Now, you'd have thought something as big as Parkes would be really good at seeing fine detail. No. It's all down to the wavelength. Optical wavelength, we're talking nanometers. Radio, we're talking centimeters. So your eye is actually better at distinguishing detail than a radio telescope. But we can use tricks, mathematics, and a hell of a lot of computing, and then we can do it. And what we do is we put lots of telescopes in a line, and it's called very long baseline interferometry. And this baseline comes up under the equation. Now, Australia's a nice big country. We're about 3,000 kilometers across. Now we can really start to see some fine detail. the SKA is coming to Australia. And I'll talk a little bit more about that. But what do you need to build a telescope? Well, you need to be away from radio interference. Some of the worst offenders, mobile phones, the Wi-Fi that we're using in this room. We need nice, flat, open spaces because telescopes don't see well through mountains. On top of mountains, they do really well, but through mountains, we're not so good at. Dry, geologically stable. There's an awful lot of electronics in one of these. Good global location for astronomy, that's easy. We draw a line at the equator, anything south, because the southern hemisphere can always see the galactic core. Access to high-tech industry and infrastructure, yeah, we're good. Access to technical and scientific staff, hello, that's you lot. And finally, a stable economy and government. 4 countries pitched for it. China, sorry guys, you're wrong side of the equator, really. Argentina, yeah, you're not so good at seeing out to the west, are you? Those things called the Andes are in the way. South Africa and us in Australia. Got shortlisted to us and the South Africans. The Chinese are now building their own in an old volcano, 500 meters across. Brilliant piece of, stunning piece of engineering. So, the Karoo and Murchison. We'll be going across Australia into New Zealand. They're going to be a little bit ambitious. Namibia, Botswana, Madagascar, Mozambique, and out into Mauritius. Last year it was decided they couldn't separate the countries. So we're going to share the project. We'll have one observatory on 2 sites using 3 different technologies. Low-frequency aperture arrays will be here in Australia. Now, these are artist renditions. This is real. This exists. It's run out of Curtin University. We West Aussies should be proud because this is one of the best telescopes on the planet already. And this is just a pathfinder to prove the way we can do this. This is useful for looking for first light. So we're looking deep back into time. When the stars actually turned on. Who turned on the light switch? How did the light switch actually get turned on? Mid-frequency. Could be aperture arrays, could be dishes. This is a picture of the ASCAP telescope. This is good for seeing galaxies that are near to us, reasonably far away. And then finally, we go to the high frequencies, which is what will be in South Africa. So this will be looking at doing the detailed looking at things. So, the first thing we need to do is design this thing. 10%. So a lot of the numbers I'm talking about are only 10% of the final product of what it could be. So, in WA, we're going to be putting about another 100 MWAs. We'll have 96 dishes out there because we are a really good low-frequency site. In Karoo, in South Africa, they're going to be putting up around 250 of their dishes to do the detailed pointing, because theirs is a good high-frequency site. The full SKA, which won't start for another 7 years, we've got time on our side, we effectively put another 0 on the end, and here. Now, the key constraint for most of that is going to be how much money's left in the piggy bank. And all the details for phase 2 will be based on what we learned from phase 1. So the 2 things we're going to be doing, mapping the sky and then looking at detail at what we find. So in Australia, we'll be mapping. That means scanning the sky very, very quickly. Huge amounts of data coming in. The South Africans will then look in detail at the objects. And again, huge amounts of data coming in. Now, this is how we form an image. We actually, using those long baselines, we use the Earth's rotation. And we have to do what's called correlation, where all the telescope images are correlated with every other telescope. So if we've got 1,000 telescopes, you've got an n-minus 1 problem. That's an awful lot of correlation that needs to go on. All right. Next prize. Can anybody see the moon? This is a radio image, and the moon is on there. This is from the Murchison Wide Field Array, and Ben Kimberley did the work. Anybody see it? No? You see the moon? Whoa. Hang on. The moon's a cold dead rock. We're seeing radio here. How are we seeing radio from the moon? What's your favorite FM radio station, guys? It's FM radio, bouncing off the moon and coming back. Now, I mean, you've only got to go out past Armadale to lose FM radio in Perth. Now, brains on danger money, because we're going to see some numbers now, and we start remembering terabytes, petabits per second. The music's really irritating on this one. So, this will be the type of thing we see in South Africa. Dishes scattered across the Karoo. Okay. 300 terabits a second. If we go with the phased array feed, and I'll talk about that in a minute, we're possibly looking at 3 petabits a second of data coming out of these things. That's a lot. This will be here in Australia, the sparse aperture arrays. There's that product placement again. Give you some idea. This isn't actually what they'll look like now. We think that the prototype designs we've been doing, but 2.5 petabits a second, the data rates that are coming from these things. And these are the dense aperture arrays. These we won't see until phase 2, possibly. It's being prototyped in the Netherlands at LOFAR. And again, we're talking staggeringly big data rates to do this. Now, remember I was talking about long baselines, having lots of these stations as we go across the country. All right, so there's all our data feeds. Now watch these numbers grow as we move further out from that core. Now, this is a country-neutral video, in inverted commas, because it has to be South Africa and us. But the Australian-New Zealand group, we go into New Zealand. That 3,000 is 5,000. We are talking some huge, big numbers. Now, remember I said we need radio quiet. How quiet does it need to be? Usually I use a feather, but I will use a piece of advertising, the Linux conference sticker. I dropped said sticker onto the floor. It imparted some energy into the ground. Did you feel it? No. I mean, we're talking less than 30 microjoules. Well, that's actually more energy than all the radio telescopes on the planet have ever recorded. That's how quiet we need this thing to be. But we're really lucky. We live in a big state. And it's always worth any Texans looking in, 8 Texases fit in WA. We are big. There's the Murchison. Now, you can tell from the accent, I'm originally English. The Shire of Murchison is nearly bigger than England. It's half the size of Tasmania. It's 41,000 square kilometres, made up of 26 pastoral leases. For you Texans out there, you are only 696,241 square kilometres to our 2.5 million. But it's got a population density of 2 millippeople per square kilometre. Because there are only 114 people, according to the Australian Bureau of Statistics, living in that shire, which means it is really radio quiet. Now, let's put it into some context. There's the Netherlands, the world, Australia in general, Alaska, Midwest. There's Greenland. Murchison's down here. It is one of the most sparsely populated areas on the planet. Apart from at the moment, because we've got loads of CSIRO engineers putting the telescopes up. Doing the wiring, the cabling. Do you know what the biggest problem we have with cabling up there? For a prize. Pardon? No. Oh, it is, but that's not really actually the biggest problem. No, it's actually a biological problem. Meh. Goats. Goats eating the cable. So yeah, we have to, everything is being buried. But goats eating the cable. And you can see here the Murchison wide field array and the tiles being laid out. Very, very nice control building. Brilliant piece of work from CSIRO, this thing. Red dirt. I mean, we're used to that in WA. The air pressure inside that is higher than outside, so the dust can't get in. But some of the work that we're going to be doing, two of the surveys, Dingo and Wallaby, we'll be looking at long surveys. Not just taking a picture, but going back and looking again, and again, and again, and again. You're getting the picture here, and again, and again. And that's going to cause some immense headaches for us. We also have some really complex workflows. Now, radio telescopes do not have an optical component. They are essentially an ICT telescope. It's the likes of you and me who make these things work. It's all down to the computing and crunching them numbers. I mean, at the end of the day, all we get is a voltage coming from the telescope tip, and then we process and crunch. But this is the type of complexity that we need to face with this. So, the first phase was originally planned 10%. For the first baseline, we're talking about 100 kilometers. It's all down to sort of how much is in the piggy bank. Now, the number of pixels is going to be a challenge here. Now, this is where, sysadmins who look after big data? Any of you guys? Well, you know, James, because you would work on some of this anyway. But no? Oh, God, don't need to put any, we don't need indemnity insurance. Your brains aren't going to go bang. Now, the number of spatial pixels varies depending on the science case. There are no moving parts. We can change it all in software, and that's what we do. For the dishes, we can go up to about 27,000 pixels per axis. For the aperture arrays, which is the one we're more interested in here in Australia, 28,000. That's better than my phone. Then there's the number of spectral channels. Now this is where it starts to get really interesting. Remember this science picture where I showed you that tiny little band of light that we can measure with 3 channels? Red, green, blue. Yeah, this is what we actually tend to see in radio. Thousands of channels. But actually, it could go up to millions of channels. So we could have red 1, red 2, red 3, red 4, red 5, etc. to red 500,000. Now, as you can imagine, that does put a certain amount of strain on the files, because we have to store all of this. So let's just assume some numbers. Assume maybe 40,000 channels. So we're not even doing a big number of channels. We store floating point numbers, so 28,000 times 28 times 40 times 12. So that's one image, 125 terabytes. Anybody got a disk that big? James, can we put that onto Amazon yet? God, they just, you just can't get the service companies, can you? Now, remember I talked about phased array feeds briefly. Now, this is a great invention from Australia. It's actually brought to you by the same clever chap who bought you Wi-Fi. So it's Dr. John O'Sullivan. This means, spot quiz, how many pixels do you get from a radio telescope? 1 is the correct. You've already had one. You can have another one. 1 is the correct answer. We do 1 pixel. Now the phased array feed is fantastic. We can do 16 at a time. Huge improvement. But of course that means we also have more data. Now remember we also talked about cosmic magnetism. We now need to store polarization information. Well, that adds another 5 to it. So we're now talking 625 terabytes for 1 image. And we go back and look again, and again, and again. And we add them together. Now, this is some serious compute problem we've got to solve here. And with those phased array feed, well, we get a nice big wide field of view, but the data volumes will go up by another 20. And of course, the astronomers love that. And I tear my hair out. You know, really, I'm only 22. You know, the grey is because of working on this. All right, so let's start looking again at some of the real numbers that we're talking about. Coming out of the front-end systems for the aperture arrays, you know, we're 8 terabytes a second. Is some of the sort of numbers we're looking at going into the correlator. Now, this will possibly be hardware. Pure, simple, no software involved, program gates to just get the speed and not have a huge cooling budget. Coming out of that, we're starting to get some numbers that sort of seem a bit reasonable. We go into line cubes, polarization cubes, and continuum maps. The continuum maps are about 110 megabytes a second. The line cubes, 120 gigabytes a second type. All right, so let's just quickly remind ourselves of RSI. We all remember, we're good with Tera, Peta, Exa, Zeta. Right? We need to remember these. Because if we look at the science cases, after 1 year, this is the type of raw data volumes that we're looking at, that we need to be able to store and process. 86 exabytes. Unfortunately, cut off the bottom here is another 425 exabytes of data. Best will in the world. Sorry, James. Amazon, you can't do it. Nobody at the moment could do that. Not even Google. Not even their barge in San Francisco could cope with this type of thing, we think. So we have to reduce the amount of data to sort of more manageable numbers. Unfortunately, this manageable number is 300 petabytes, but it's been cut off by the screen. But you know, we're talking serious wads of data that we have to store, so we really don't want to be moving these around. So we've got to come up with systems that can put the data down once and tend to keep it there. All right. We'll up the ante for posher prizes. Slinkies. Let's just take 3 of the science cases. All right? The intergalactic medium at the epoch of reionization, the wide area H1 emissions, and some continuum surveys. So, you know, 500 exabytes. A Blu-ray disc can take 50 gigs. It's 1.2 millimeters thick. That's a stack 13,000 kilometers high. How big is the West Australian coastline? Come on, there's a prize. Come on, boys, come on. Pardon? No, the West Australian coastline. I mean, if you start down on the south and go all the way up and run a little thing. Well, yeah, but when we're talking numbers like this at this scale, I don't think we tend to be that stressed by it. So I heard a 6, that's too low. That's too low. That's too high. It's 12,000 kilometers. Our coastline is 12,000 kilometers. Now, I mean, that would be great job creation, wouldn't it? Discs all the way around everybody gets to be by the seaside. Job by the sea. Getting discs and putting them into Blu-ray readers for us. Nah, not going to happen. All right, let's try another one. iPod Touch. 64 gigs. They're the sizes of them. There's the Olympic swimming pool at Sydney. How many swimming pools do I need to store this data? Nearest 50 will do. No, that's actually a little bit too high. Is exactly right. Well, it's 161, but it's nearest 50. Now, if you do hear us that we're going to be doing this, buy shares in Apple. All right, now back to some of the real computing component. We have changed our way of thinking. Up the top there is a picture of Gene Armdale. Modern supercomputers have the storage over here and the compute over here. You take the data, you send it to. That's not going to work for us, but it's not a new problem. It's an old problem. Back in the 70s, we had the same type of problem. I mean, we had dial-up modems then. What we need to do is get the Armdale number down to as close to 1 as we can. So you have the compute and the data as close to each other as possible. So things like Hadoop are ways of doing this. And we will be looking very, very seriously at what we can do with those types of technology. Okay, we're all familiar with this. Good old Moore's Law. That is the top supercomputer on the planet. That's number 10. That's number 50. That's actually not a bad plot, is it? You know, I mean, that's pretty straight there. A log scale on this side. Okay, we can see the big jumps here. Now let's come up to date. For ASCAP, we needed something in the top 50. And we did it. And it's here in Perth. EPIC, Fornex, Magnus are the supercomputers we've got here. Thank you, taxpayers. For the SKA Phase 1, we need something up there. Some serious iron. So, at the moment, the Chinese, bless them, are ahead of the curve. Let's hope we can keep growing like that, because otherwise we're up the Swanee. Now, this is Tanhe 2. It's Chinese word for Milky Way. It's the most powerful machine on the planet at the moment from China. So these dudes don't actually look that Chinese. That's because they're Germans. A lot of the design for it was done by the Germans. 3 million cores. how many million? Well, I think 1.3 or 2.3 million GPUs in there as well. Needs the same amount of power as 17,000 homes to keep it going. But, I mean, I can see a few grey-haired folks around here. I remember Cougar. 1 teraflop. Yeah, 1997. 72 cabinets to do that. It's on chip now. The Knight's Corner chip can sustain 1 teraflop, doing that type of thing. So, please, geeks, keep it up. We're relying on you. But we have some serious power consumption problems. To get up, we're dancing around an exaflop here. I mean, that's roughly 121 megawatts of power. So as we said, 1 megawatt is about 1,000 homes. So we really do need to sort of try and find some greener, efficient solutions to this, because this is a big problem. You face it all the time in server rooms. So that gives you some idea of the scale of the thing. We've got one of the biggest processing problems on the planet, one of the biggest storage problems on the planet. We have a huge bandwidth problem on the planet. We have a really big power budget problem with this thing. But we are working on a system that can take, or will produce the same amount of data as the whole of mankind would produce usually in a year in one day. That's a lot of data. So, what's next? Well, this is the part that gets interesting. We're now starting the design work, and it's all Linux-based at the moment. Which I suppose is one reason why I'm here. Most of the work we do is Linux-based. Literally, last week, we started work on the design for the science data pipeline. So this is the computing to move the data through. We're involved in 3 areas of it. Low-frequency aperture arrays, which have been run out of Curtin University. Signal processing, so doing the correlation, and the one that's mostly my main interest is the science data pipeline. So this is how do we move, store, process those enormous volumes of data. So we're just doing starting the design now. It's a big international effort. Teams from all around the world contributing together to build this thing. And there are industry opportunities in this. And if you don't believe me, ask that gentleman over there, because he's involved. Then from 2016 to 20, we'll build it. And again, there will be contracts going out. The way the funding works, each country has put in money to build this. And the money the country puts in goes to people in that country to develop those components. Which means that you won't see much from the Americans, because they're not involved. And then, finally, in 2020 to 2024, we build the rest of it, depending on what's left in the piggy bank. Now, we're working on some of those problems, which is why you see most of the people who come from ICMA smile a lot, because that's our job, is trying to make that thing work. Now, do you want to help? You can help from your home computer. You can help from your work computer. If you've got a server farm, you can help. If you've got an Android device, you can help. Now, the numbers for this are for ASCAP. Right, so this is the Australian Square Kilometre Array Pathfinder. Our friends in South Africa are much better at naming things. Theirs is called Meerkat, which is a much cuter name, isn't it? At least it's meerkats looking at the sky. ASCAP. Ugh. I'll have to update that now to PS4s. And that may be one of our saving things. So, what we're looking at is some of the problems that we know we're going to face. The SKA and the LSST, which is the next generation of telescope coming out of the United States, are going to have huge data problems. We know they are. So we've been looking at experiments now to see how we can solve some of these problems as they come along. So that's where we started the SkyNet 2 years ago. POGS is the main thrust of this now. Pan-STARRS Galaxy, Optical Galaxy Survey. What we're doing is we're taking images from the Pan-STARRS telescope, Galax telescopes, WISE telescopes, merging them together, and then we do a spectral decomposition of each of the pixel points. Now, it takes between 5 and 10 minutes to do one pixel. We want to do about 100,000 galaxies. Well, yep, that would be between 1 and 2,000 years if I did it on my little Mac. Can't wait that long. So we've used the BOINC infrastructure to do this. So things like SETI at home, protein folding at home, those types of technologies are what we're using here. We're even publishing on it. First papers are out on what we're actually up to with this. As of today, we are into our 11,000th galaxy. So we're nearly a tenth of the way through this as we process through. Basically, it's citizen science. From this, we then want to be able to get things like bulge disk ratios. We want to be able to look at scale lengths, break radii, how galaxies form. So all this computing and number crunching actually does give us some real science out the end. There's the website. Unfortunately, it's cut off at the top, which is a shame. Google POGS, theSkyNet. Join up. Even tweet me. You know, that's the piece we want people to join, to go in to see this thing. And we've got a fairly pretty interface, all runs in the Amazon cloud. But why BOINC? Well, this is Titan. This is the second most powerful computer on the planet. Has to be the second one because I know how much that one costs. I don't know how much the Chinese machine costs because that information doesn't tend to be generally available. 97 million US for this beastie. Well, all the BOINC projects on the planet together come to about 8.3 petaflops. And that's a hell of a lot cheaper than $97 million. As long as latency isn't a problem, you can use this type of technique. Now, it actually runs in the Amazon cloud. All of this is Amazon-based. This is the old architecture that we had for it. Didn't really trust them. They gave me $2,000 to get it started, you know, to try and lure us in to see it. So we went with a simple solution that we could move out. Well, actually, we didn't. We've bought into even more of it now. We have on-demand AMI instances firing off as we need them to be able to cope with scaling. We can scale out enormously. Starting on the 18th, we've got one of the biggest challenges, BOINC challenges, hitting us. William Herschel's anniversary. 18 international BOINC teams are coming to us to see who can process the most work units in a 2-week period. So teams from Russia, the States, the Scots, the Australians, the French. All of these teams are coming in to do just this. And we're running the whole thing on a Linux background. It's so simple to do. It's also got some nice pretties. Now, this is M100. The pixel sizes, I mean, they're reasonable size images we need to process here. And what you can see here, this is the star formation rates, the dust reabsorption, and we try to get people involved so you can collect galaxies and show where you've been. There you go, that's the star formation rates in M100. Now, needless to say, they're false color images, and they're obfuscated, because I don't want other people using my science until I've finished with it. So we do obfuscate it a little bit. I mean, we tend to work, though, in a black and white. And the little gaps you can see, Well, that's bits that we haven't actually got processed yet. We can keep on going doing this. I mean, it's one of the joys of working with a big cloud-type system. It doesn't matter if it's all finished. The bits that you have finished, you can use. But finish on a cautionary tale, shit happens. This was in the middle of a challenge earlier this year. You can see we were maxing out one of our machines. The other was pretty heavily stressed. Crash. Lost a file server in Amazon. Now, it doesn't happen very often, but did to us, unfortunately. Fortunately, the back was raided. So you can see the time it took me to get it up and running again. And running a much bigger instance this time as well. Dial up more compute power. But standard operating system and sysadmin type techniques scaled really well with that. So that gives you some idea of the type of things that we're going to be doing in big computing space. Anybody any questions? Fire away. Oh, hang on. Somebody's waving and pointing at that they want the mic. Now,
Getting that? It's on now. Might not have battery. Oh, did it? Okay. Can you hear me? Cool. Sorry. So, how are you doing data validation on all the BOINC clients so that people don't embed alien signals in your data?
For the BOINC stuff, we don't need to because it's images that are coming straight through. But what we do is we cross-check them. So we don't take one image as gospel. I don't trust most people as far as I can spit a dead cat. So I'll cross-check it against many others. And then when I've got a number of them that say, yep, that's the same, I feel much more comfortable that, yes, it is that value and not somebody playing silly beggars.
Cool. And so that's all done in software? Or
Yep.
you say I look at it, but...
No, it's all done in software. Yeah, I wrote the software. So
And sorry, I might have missed a slide. Is that open source? Like, can people
yes,
look at that?
it's
Cool.
all on GitHub.
Oh, awesome.
You can go and find all of this under ICRA BOINC Mag Fizz.
Cool.
So yes, it's all open source, the whole kit and caboodle.
Awesome.
Simple one, obviously not for myself, but I assume you're hiring?
No,
You're not? Oh!
we're working with partners because it's being funded by the state government and federal government. We have a constrained budget. We have enough money now that will take us through to the next phase and cover salaries. I will be writing an awful lot of grant applications over the next couple of years to get the next parts of it going. But we are working with local industry on this project. Part of the conditions for the ICRA 2 funding were we had to involve local industry. Well, that's not a big deal. You know, we've got people like ThoughtWorks here. We've got Amazon here. It's really not that much of a difficult task to think, well, yes, let's involve these guys. But we're also going to be involving the likes of Intel, Cisco, DDN, the big players, because at the end of the day, we need to know what their hardware's going and what their roadmaps are to be able to say, well, in 3 years, where do we think we're going to be going?
So, what's the criteria for local industry?
Well, there was a proposal went out 8 months ago, 9 months ago.
Yeah.
People needed to reply to it.
Cool.
Come in. We say, yep, fine, if you've got something that can contribute to it. If not, well, not many people actually did it. I mean, most people look at the numbers and go, well, yeah, I can do an insurance website for you, but that type of stuff, nah. It's very, very specialized work.
You said that power consumption was a big problem for these large supercomputers.
Oh, and
but
how? I mean, we
what-
need 50 megawatts up at Murchison alone. I mean,
But What is the power consumption of these distributed system, like the SkyNet? Because presumably all the nodes which are doing the computer are much less efficient than these large supercomputers.
But we've effectively pushed the cost out and
Someone
the
else's
cooling out.
problem.
I mean, don't forget, with most supercomputers, it's not actually the power to drive the things; it's the power to drive the air conditioning and to keep them cool. I mean, that's why a huge number of the big cloud companies are going to places like Oregon. Greenland has actually started to talk about using. I mean, they've got tons of cold water straight off the glacier. So if they can do that, then they can bring the power down. But some of the calculations we've done for the Palsy Centre, which is the hub that's run here in WA by IVEC, if we took the low-grade hot water that comes out of it, it's just about the right temperature for a microbrewery. So we could be seeing SKA beer or computing beer coming out of that. Pardon? They might be asking for tasters. Any other questions?
Just in view of the new government we've got, how secure is your budget?
That's a
rather
political question which I will
anti-scientific.
avoid totally. I know I'm not a politician, I'm a scientist.
So are you sufficiently international that it's not
Oh.
going to bypass our own...
For the SKA, yes, we are. I mean, it's run out of Jodrell Bank in Manchester. The Australian government have committed. I mean, we have two aspects. The Liberal Party here in WA are fantastic. They are completely behind this. Colin Barnett has put an awful lot of his own time and effort into making sure this happens. Federally, perhaps it's not the same story. I mean, if you looked at the images that I showed where it showed where we were looking at putting the nodes as we moved across the bush, they're actually where the fibre goes on the NBN. Let's hope the fibre goes there, because if it's wired to there, we're dead. But it's started its move. I mean, we have the commitment from the government now, so the money is there. We're starting to move on it. As the next phases kick in, well, we'll have had another election by then. The previous government, again, they at a federal level, they were fantastic. I mean, I don't know whether it was urban myth, but it sounds good. When the SKA were evaluating the proposals, one question they sent back to us, the Australian government, was, will we have to pay GST? And they got a personal note from Julia Gillard that said, no. That's how they were behind this. I mean, they really wanted to see us win this.
Great, thank you.
Any other questions? No? Oh, one more. Absolutely. The type of architectures we're looking at, that's why the supercomputers we have here in Perth are very different from each other. EPIC, which is at Murdoch, is a classic multi-core machine. So basically it's a shipping container full of x86 type chips. Fornex, which is at UWA, is 92 GPU based machines, because when all said and done, what we're doing here is mostly floating point math and lots of it. So the biggest headache we're getting there is where the bottleneck is. The compute now isn't a problem. It's getting the data in through the PCIe bus, which, I mean, PCIe is very good, but it's still not good enough yet. We're going to need something else as we go through. And then the new machine, Magnus, is a combination of various components. So we've got a Cray going into it. We've got a very nice hierarchical storage management system, so we can store about 2 petabytes and have it moving through cascading layers to a tape system as well. All of this was specifically bought with radio astronomy type work in mind. I mean, it's to service a much wider community, but And we had a fair amount of say in the types of things that would be needed. And therefore the experiments we need to do with this type of data. And we also have the old standby, if we need 1,000 nodes quickly, Amazon. Though we do use America, not Australia. Most of my audience is in the States and Europe, so going into Virginia is actually easier for them than going to Sydney, because the pipes into there are big, but the pipe across out of Australia is not that big.
Do you see a potential for using FPGAs more to save power? And
certainly in things like the correlator, yes. But the problem with them is once they're there, they're there.
Pretty dedicated.
And things like correlation, I mean, the improvements in it happened much more slowly. But for the general type of software, now real software is better because we can change, we can tweak. We can improve algorithms. I mean, if you're talking, say, 3 million cores, replacing 3 million FPGAs is a bit of a task. But if you're just pushing out software, you can do that fairly quickly. Well, some of them can nowadays, but when we were starting to look at it, but again, the other problem is, there was for a while a very, very good supercomputer called Roadrunner, which used the PS3 cell chips. And very few people could use it because it's a pigged program. And that's another problem with FPGAs. That is a very niche area, and they are pigs to program. If you're good at it, I'll take my hat off to you. But that's a very, very small market. And we don't want to be in the same position, a lot of businesses are, where the only people who can do it are the old COBOL programmers who are charging an absolute fortune because, hey, I'm an old COBOL programmer and I can now earn a huge amount of money because no other bugger can do this. Oh, absolutely, but so are these. I mean, these things are driving power saving because we're trying to put, we as consumers, I want to run more and more on here. I want to be playing Angry Birds and not have my battery die in 20 minutes. I want to be able to have a phone call that lasts for an hour or so without it dropping out because the power's going. Well, the consumer electronics companies are being driven by us to do that. And of course, that will then flow into the design for the bigger machines. I mean, there's absolutely nothing stopping us going out and buying 1 million of these and plugging them into one hell of a big USB thing. Store the data on and send the program to it. So, the ultimate Hadoop cluster using iPhones or Androids or, so yes. Pardon? Yeah, I mean, the Android would probably be an easier one because it's much easier to get in and do things with. And as we saw with the POGS stuff, we actually have an Android version of that because we can do that one. iPhone is much harder because the original code is good old Fortran 77. Hey, there's a few people who remember that in there, nodding heads. Yes, well that's what it's written in. And it's one of those great examples. I've actually cut some of the code out to use in computer science lectures to say, and this is why we don't use go-tos anymore. Let's see if you can figure out how this integration code works. It's been evolved over time by a number of people, and it works. Black box it, put a wrap around it, and write "Do not touch." Yep. The NBN, some of the first NBN cable was between Geraldton and Perth. There's a huge dark fibre bundle in there, but of course the photoelectronics, optoelectronics is the expensive part. So I think we've got 4 fibres lit at the moment, CSRO control all of that, and I think it's something like 40 gigs we've got provisioned at the moment, so we can light more and more as we need it. But yes, it's all the way to Murchison and back down, and it's working. With the MRO for the Murchison wide field, we're sustaining, getting on for about 40 megabytes going through, and we're then replicating it to Massachusetts. So, I mean, this is all part of the precursor. You know, we are doing experiments to see how we can do it for the real McCoy when it comes. So, yep, we're starting to get there. We've got bits that work, and it's a real application. You know, it's not pie in the sky. These are real. And they're now commissioning ASCAP, so we'll start seeing that data coming through too now. Some beautiful images. Any more? No, we would do the distribution from Perth rather. Now, I mean, as I said, we're looking at the designs now. You know, I mean, some of the things that are on the table are things like the way the Large Hadron Collider did it, where you have stage 1, stage 2, stage 3, and you push the work further and further out, depending on what the needs are. You know, if it's something that needs to be done really quickly, it goes to the more important nodes. If it's something that doesn't, you can then push it further out, and it can take a little bit longer to do. Yeah, essentially. And, I mean, that's how LHC's been doing it. And it worked. And the Higgs boson was found, and a Nobel Prize was awarded. Well, the correlator we may well have at Murchison to try and reduce that coming down. So yeah, no, we may well, the decisions are still up in the air, but the chances are, yes, the correlator will be based at Murchison. And again, that's another reason why FPGA is in the correlator, because power to Murchison is a problem. Pardon? Well, and I mean, at the moment it's diesel generators. And there's talk of looking at a spur off the Dampier to Bunbury pipeline, have their own gas-fired power station. I mean, these are sort of options that have been put onto the table and will be explored, because it is a major problem. How on earth do you generate enough power there and generate power that doesn't interfere with the telescopes? That's an interesting area of research where we've had a little bit of success lately. Slava Kitiev at ICRA has been looking at this. At the end of the day, a lot of the value is noise. And we're looking at how we can store it inside of what's called a FITS file. Now, the FITS format comes from NASA. It was invented in the 1970s for tape, and is still in use by the astronomy community. But what it does is it uses an offset and then puts the numbers in. So we're looking at that type of thing, because a lot of the data has a random pattern to it, and it just doesn't compress very well. But if you can truncate off chunks of it and not affect the quality of the image, well, that's easy then. You know, we can knock 50% off just by cutting those noisy bits off the end. But everything depends on what your data is and what you're looking at. So each science case would be different depending on it. And I mean, other things, JPEG 2000 has got some good elements in it that we're looking at as well, and how we could use that. Yeah, but if we can, we will, because it just reduces the amount we've got to move. You know, particularly when we think once we start pushing out internationally, big winners then are the telcos. Cha-ching, as if they don't make enough money already.
Just talking about that again, do you plan to store the stuff for any length of time, or process and dump?
There would be two aspects for it. What we're looking at for the data as it comes straight off the telescope, if something goes wrong, we dump. We can't store it to process later. We just haven't got the capacity. But once it's been reduced, it would then be stored and archived, and there will be a big metadata component that goes around it. I mean, we've got PhD students who are working off photographic plates, looking at supernova expansions that were taken in the 1930s. I don't know what my grandchildren are going to be looking at. There could be a supernova tomorrow, and it could take 60 years before it gets interesting. And they're looking at the shocks on it. Well, we've got to try and save some of this data to pass through. And that was one of the good things about photographic plates. You could put it somewhere nice and safe, and there it is. If we lose all the cores, or we get a nice huge EM pulse.
Yeah, I suppose the big risk is that some of the stuff that you're stripping may end up being valuable.
It could be, but bearing in mind, I mean, what we're doing is integrating the signal over sort of 8 to 10 hours. We'll have flattened out if there was any sort of thing in there, aliens trying to send us a message, or adverts from Alpha Centauri. We wouldn't see it. It would just be, there is a spike there. We can see something in that signal. Because we're looking at such faint signals still. Things like Lorimer events are an interesting problem. The area is being handled by another group, and some of the things they're looking at are really quite clever. So it would be sensing sudden changes in frequency across many domains, and then, yes, that will just dump. And we'll look at that later. But it's a huge dump that's going to be coming down. Because yeah, and it's a whole area that has got a lot of people working very hard, and it's being done by other groups, not us. But yes, it's an area that's going to cause some very interesting work. I mean, how on earth do they do that? It's almost like a sluice gate. Or, well, not a sluice gate so much as duplicating down before this lot is off being reduced. But we need to keep this lot for subsequent analysis. Yeah, could be anything, and that because it's going to take time for it to go through all the stages. I mean, it could be 2 weeks. Then you come back and you've got to go and say, all right, let's go and have a look what on earth that was, because we have to do all the quality assurance checks on it. Is it real? Is it actually something there, and it's not just bad data? Quite often, you saw when I was showing the video from the guys from Astronomy, where they were showing how we build the images, you saw the artifacts that were being built by the building process. Well, you have to get rid of them first and make sure it's not just something daft. And the last thing we want is sort of the embarrassment of neutrinos going faster than the speed of light. The Russians have already got an orbital radio telescope. It's up and it's working. I mean, the problem we'll be looking at is the baselines, and we want to be able to do. It's cheaper when all's said and done to build it here, and that's the main driver. Cost. Yep, they've done a staggeringly good job. I mean, it's up there, it's getting data. But if we had to put 100 to get a really long baseline, I mean, that's 100 launches of satellites. Well, because of the angular resolution. Remember the equation, lambda over we would want to have, I mean, it could be a damn great big one, but can you imagine a rocket that put a dish up that's, 64, well, POGS is 64 meters. The Chinese have got one that's 65. But launching something like that, it's beyond our capability at the moment. But bless them, the Russians are the only ones who've still got something really that works. The Europeans have got their stuff. The Indians are now coming into the market as well. So, yes, I mean, it could be, but it's still damn expensive. Well, yeah, but it's commercial space race now, isn't it? I mean, you can go for a flight in a Virgin plane up there at if you're not a geek and earn a decent salary. But for those of us in this room, it's not going to happen unless we win the lottery. No, we use it. Well, the work's been done by the quantum labs. Some of the work's been done by the guys at the quantum labs at UWA. So they're sapphire, diamond, atomic clocks. Because we've got to be very, very accurate, and all of them. Because we have to remember, we've got some telescopes on this side of the country, some telescopes on the other side of the country. When that photon hits there, it's going to arrive here a little bit later. And we actually need to know that delay very, very accurately because we have to allow for it. So when we're doing the correlation, we're not saying it's exactly this time. We're allowing for all those time shifts to give us the right image. So very, very accurate clocks.
Can you use some of the background sort of stable pictures to actually use to calibrate that rather than trying to time it?
Well, calibration is always a changing thing because it depends on time of day, the atmosphere. I mean, things with a radio telescope, you tend not to observe at dawn or dusk because the atmosphere gets all messy and basically what you see is garbage. So we have to be very careful about that. But there are certain things that we know and we can use as a pointer, but it's always changing. Just another problem among all the others that we've got.
Great. Well, thanks very much, Kevin.
My pleasure.
Yeah.